Although we know a lot about light, there are still some mysteries as to how it is truly structured and functions. In this installment of the Primer Fields, we will reveal the true structure of light and thereby unlock some mysteries that have perplexed the world's brightest minds for centuries. You will be shown what is truly behind the dual nature of light. It will be revealed why light has the properties of both a particle and a wave. In other words, it will be shown why light can be proven to consist of discrete units known as photons, and yet have wave properties at the same time. Then we will see this same structure would apply to all electromagnetic radiation as well as all matter. This explanation will also reconcile the infamous double-slit experiment in a way that most anyone can comprehend. Since the double-slit experiment is at the core of quantum mechanics, this has profound implications for the future of quantum computing as well as many other future technologies that will be built on this knowledge. Some of this future technology is already here, but that will not be revealed until Part 7 in the Primer Fields series. In this installment of the Primer Fields, we will discuss edge diffraction, single-slit diffraction, dual-slit diffraction, and many other aspects of light as well as all electromagnetic radiation. The interesting thing is that the explanation to all of this is actually quite simple, and as you may have guessed, it is built on the Primer Field structure. So let's start to unravel our little mystery. In this demonstration of the dual slit experiment, we see a red laser, a yellow laser, and a green laser being used to show how the different wavelengths or colors of light respond when they pass through identical double slits. This experiment clearly shows the wave nature of light, and yet we know from other experiments that light is made up of discrete units, or quanta of light, that we refer to as photons. Notice how the patterns of the three different colors vary. This is a very important clue. Then with single edge diffraction, we see the very intriguing patterns around the edge of the razor blade. This is another very important clue. We also have important clues revealed in the continuous spectrum of light that is shown in these single slit experiments. Experiments that have been undertaken with electrons also have left us with some important clues that will also help us solve this mystery. This chart shows the frequency, wavelength, and energy levels of electromagnetic radiation. This is yet another clue. This is a diagram of the electric field and the magnetic field of all electromagnetic radiation. One more clue for us to use. Here we have the structure of one unit, or quanta, of electromagnetic radiation. The red field is of north polarity and the blue field is of the opposite polarity. Then we see how this structure would fit into our diagram of electromagnetic radiation. So the size of the fields is determined by the wavelength of the electromagnetic radiation. Therefore, the field size is equal to one cycle of the wavelength, with the zero crossing point being centered on the nucleus of the fields, or photon in the case of light. Now we are going to take a look at the internal flow within this single photon. Again, this would apply to all electromagnetic radiation. The green sphere represents the photon. Here we have the internal energy flow within the fields of the photon, as well as several other views of the photon and its fields. The image in the upper right corner shows how this is related to our vacuum chamber experiments. The same flows are at work in the vacuum chamber. Now around the core of this photon we have the bowl-shaped magnetic field emitters that were first revealed in the Primer Fields Part 2. Then as we zoom in on the core of our photon we see the flip ring and the choke ring. Then notice that the incoming particle flow is not just particles. Each particle flowing within the photon's fields also has the same bowl-shaped magnetic field structure to it as well. So these flowing particles are not really particles at all. They are actually concentrations of energy. These flowing concentrations of energy also have the same internal flowing structure as the photon itself does. The photon is actually a concentration of energy made up of many flowing concentrations of energy, which are made up of many flowing concentrations of energy. How many levels down this repeated pattern goes is unknown. The green circle in this image represents the concentration of energy that we refer to as the photon. But as you can see, there is a lot more to the photon than just the energy concentrated in the middle of the photon's fields. The exact size of the photon in relation to the fields and where it is exactly in relation to the flip rings still needs to be determined. This image is only meant to give you an idea of the overall system and not meant to be an exact scale model. In reality, the photon is much smaller in relation to its fields than shown here, but this ratio is more effective for showing the inner workings of a single photon. After the incoming concentrations of energy hit the flip ring, they become trapped inside of the green circle, or photon. But as you can see, some of this trapped energy escapes at the equator of the photon and is recycled back into the flip ring yet again. This is the same pattern that we see in the vacuum chamber experiments. Now let's take our single photon and its fields and put them in a single row with other photons. Remember, the actual fields that are shown here in red and blue are actually invisible. The green spheres are the photons themselves. The red fields represent north magnetic polarity and the blue represents south magnetic polarity, and therefore they are naturally attracted to each other, and the spacing between the photons is maintained by this field structure. Now the photons will go by us just missing us, but the fields of the photons do hit us. In the real world, this of course would make the photons turn slightly because of the drag on the fields on the side of the fields hitting us. Photons can be turned by an obstruction in the path of the photon's fields, even if the obstruction does not contact the photon itself. This is how light can bend around an object. Also remember that each photon's field structure has the flow shown in the lower left corner. Again we see the diagram of electromagnetic radiation, and you can clearly see how this diagram agrees with the structure of our photons and fields. So the ball of confined plasma in the vacuum chamber has the same basic structure as a photon. Now let's take our white photon and split it up to give us 6 different wavelengths, or colors, of photons. The photons are now shown with the relative sizes and spin rates. This animation is just an approximation to give you the basic concept and not meant to be an accurate scale model. The important thing to note is that the smaller the photon, the higher the spin rate. This would apply to all electromagnetic radiation. The violet photon has a shorter wavelength than the red photon, and it also has a higher spin rate. The violet photon also has a greater energy level than the red photon. Therefore, the shorter the wavelength, the higher the spin rate, the greater the energy level, and the smaller the photon. This would logically apply to all electromagnetic radiation. Then, of course, the wavelength is related to the field size, and the field size is related to the photon size. Let's do a quick review of the internal flowing energy structure of a single photon before we move forward. The flowing structure is the same for all electromagnetic radiation. Once more, we see that wavelength is related to field size. Here we have rows of photon fields with the corresponding waveform. So you can now see that the waveform clearly represents the size of the fields around a photon of electromagnetic radiation. Now the fields are shown as red and blue polarity fields. This image represents what happens to the fields as a row of photons pass through the glass. Notice how the fields are compressed as they pass through the glass. Remember that the fields are actually invisible. Now we have a row of photons that we are going to observe as they go through the glass. Let's attach a light speed indicator to one of the photons to keep track of its speed. Watch as the photon decelerates as it enters the glass. Then the photon accelerates back to full light speed as it exits the glass, and the other photons in the row also accelerate back to full light speed upon exiting the glass and re-establish their normal spacing. Now we are going to have a race between two rows of photons. Only one row of photons is going to pass through the glass. Notice how the fields of the bottom row of photons are compressed as they encounter the glass. Then as they exit the glass, the compressed fields rebound and push the photons away from the glass, thereby re-accelerating the photons back to full light speed. Let's have another race between rows of photons. Once more, we see how the compressed fields rebound as they exit the glass, thereby re-accelerating the photons to full light speed. This compressed field rebound is what is responsible for the movement of the optical fiber in the video to the upper left. So as the photons and their fields pass through the optical fiber, they compress like a spring. Then as this spring of photons and fields exit the optical fiber, they rebound and push off of the optical fiber, causing it to whip very slightly. So as you can see, light actually pushes off of glass as it exits the glass. Even the photons of light that are hitting your retinas from this video are being pushed off of the screen as they leave the screen because of the rebounding effect of the compressed photon fields. Then again, the size of the fields of a photon are determined by the wavelength of a photon. Here we see the typical waveforms that are used to represent visible light and other forms of electromagnetic radiation, but in reality, no such waveform exists. The waveforms are useful for discussing electromagnetic radiation, but light and other electromagnetic radiation does not move in a waveform pattern. In other words, light does not go up and down, or wiggle. Once more, we see that one wavelength is equal to the size of the fields. In this image, the upper row of photons are shown enlarged so that you can see the spin rate and relative size more clearly. I have also intentionally shown the upper photons as not having a hard spherical shape to emphasize that photons are actually concentrations of energy, just as the ball of plasma in the vacuum chamber is. Now we are going to see why light of different wavelengths have different angles of refraction. In other words, why we get a spectrum of colors when we shine white light through a glass prism. In this animation, time is frozen temporarily, and this has stopped the photons moving so that we can get a better look at the dynamics of this glass-photon interaction. As the row of photon fields enter the glass prism, we see that the different colors refract or bend at different angles. Then we see that as they exit the glass prism, the photon fields also refract at different angles according to the wavelength or color of light. Clearly the light refracts at the surface of the glass prism, and the photon fields highlighted in white are what we want to focus on. Now we are going to watch as two photons and their fields travel through the glass prism. We can clearly see that the violet photon fields refract more as they cross the glass prism surface than do the red photon fields. Then as the photon fields exit the glass, we also see that the violet photon fields refract more sharply than the red photon fields. This time we are going to zoom in to watch as the photon fields enter the glass prism. You can clearly see that the violet photon refracts more sharply than the red photon due to the size of the fields. So the smaller the fields, the more sharply they will refract. Since field size is related to the wavelength of the light, this agrees with what we actually find when light is refracted by a glass prism in the real world. Let's watch as the red photon fields enter the glass prism. Notice how the leading edge of the photon's fields hit the glass first, and this turns the photons as it enters the glass. Then as the photon enters the glass, the fields are compressed, just as we saw in the photon races we ran just a bit earlier. Now as the compressed fields exit the glass, they rebound. Since one edge of the photon fields exit the glass first, it rebounds first, thereby pushing that edge of the photon and turning the photon and its fields. Again, we see the red and violet photon fields as they pass through the glass prism. So now you know why light refracts as it passes through glass or other transparent materials. It is very simple once you know how photons of light are actually structured. Again, we see that the fields around a photon are of opposite polarity. Here we have some rows of photons aligned with their corresponding waveforms. Now we are going to overlap the rows of photons. When waveforms align with each other, they are referred to as being in phase. When the waveforms are not in alignment, they are referred to as being out of phase. When the photons' fields overlap in phase, the red polarity fields line up with each other, and the blue polarity fields line up with each other. This results in an increase in energy, and the photons shine more brightly. This is referred to as constructive interference. When the photon fields overlap out of phase, the fields of opposite polarity line up with each other, and the energy flow of the red field cancels out the energy flow of the blue field. This results in no energy going to the overlapping photons, and they therefore emit no light. In other words, both photons go out when they line up out of phase. This is referred to as destructive interference. As the photon fields continue to move, we see the constructive and destructive interference. This is why the light either goes out or gets brighter in laser interference experiments. You can see that this is not a simple on-off situation. The more the overlapping fields line up in phase, the brighter the photon will shine. Then the closer the fields line up out of phase, the more the photon dims. This is why there are not sharp cutoffs in the interference patterns. There is a gradual transition from light to dark in the interference patterns because of this effect. Now we have two flat panels of photon fields. Notice that the panel of photon fields on the right can rotate. In reality, the overlapping fields would result in no light at all, but the limitations of the animation software I use would not allow me to achieve the effect I desired here, but you get the idea. Now watch what happens as we rotate the one panel of photon fields. Now let's get to edge diffraction. Notice the intriguing patterns around the edge of the razor blade. This animation shows a photon gun that will emit a single row of photons across the yellow edge. Notice that the more the photon fields hit the edge, the more the photon and its fields are refracted. The photon itself still goes by the yellow edge, but its path is altered because of the drag of its field going across the edge. So if we have photon fields crossing the yellow edge at various levels, we will get a range of diffraction, as shown here. Then as these diffracted photons cross each other, we see our interference patterns emerge. This is the reason we see these interference patterns around the edge of the razor blade. Now we are going to discuss slit diffraction, which is basically just edge diffraction, but with two edges that are parallel to each other on opposite side of a beam of photons. As you can see here, the widest slit results in the narrowest pattern. A greater percentage of the photons passing through the narrow slit are affected by the edges of the slit than is the case for the widest slit. So the edges of the wider slit affect a smaller percentage of the photons passing through the slit than would be the case for the narrower slit. In this demonstration provided by MIT, we see a red laser shining on a single slit, which will vary in width during this demonstration. So as the slit width increases, the pattern becomes narrower. Then as the slit width decreases, the pattern gets wider and more diffuse. Here we see our photon gun again. But this time our photon gun has been modified to emit two rows of photons with their fields at the same time. A single slit gives us a fan-shaped pattern of photons and their fields. Now let's see what would happen if we had two slits with photons passing through them. The distance between the slits is varied so that we can observe changes in the interference pattern. These interference patterns are the result of constructive and destructive interference. Now you know the true cause of the perceived dual nature of light. The fields around the photon obviously result in the wave-like behavior of light and other electromagnetic radiation. But we still have an issue with the double slit experiment that we need to address. The interference pattern still shows up even if we fire single photons or single electrons through the dual slits. The photon or electron seems to interfere with itself, but how can that be? Up until this point, I have been showing you a simplified version of how the fields are truly structured in order to avoid confusion. There is a lot more to these fields than just what you have seen thus far. Now it's going to get a little more complicated as we start to discuss how these magnetic fields overlap each other and interact with each other. Here we have the photon and its fields again. But in reality, the electromagnetic fields do not just stop at the limits of the fields shown here. They continue out much further, but they also get much weaker as they go further away from the photon. Now we see the red field extending out much further than what we have discussed up until this point. Again, this extended electromagnetic field is much weaker on the outer limits than it is next to the photon. Now we see the extended blue electromagnetic field. The further you go from the photon, the weaker the fields. Notice the interesting similarity to the wave function of hydrogen 421. Now we have two photons. Now we have the extended electromagnetic field of these two photons. Notice how the extended electromagnetic fields overlap each other. Here we see the extended fields represented in wireframe. Now we see the extended fields overlapping each other. Let's add some photons and fields so that we have a row of photons and fields. Here we have one set of extended electromagnetic fields, and then two sets of extended electromagnetic fields. Now we have all of the photons' extended electromagnetic fields. You can see why I have avoided discussing these extended electromagnetic fields until now. But the way in which these fields overlap is very important when it comes to understanding the double slit experiment and how the bonds in matter can be so strong. So you can see that the extended electromagnetic fields extend well away from the photon, just as the fields of our Sun extend well out away from the Sun. The fields of the Sun extend out past Pluto, and even that far from the Sun, the solar wind still carries charged particles. So you could think of the Sun as a giant photon. Again, we have a single photon with its extended electromagnetic fields. One of the most intriguing experiments in physics is the double slit experiment. Until now, there has been no satisfactory explanation for the interference patterns that result when you fire only one photon or one electron at a time through the slit. It is as if the photon or electron interferes with itself. But this apparent paradox is resolved when you understand that photons and electrons are not just balls of condensed energy. Photons and electrons are also surrounded by their electromagnetic fields that are much larger, and there is energy flowing in these extended electromagnetic fields. The photon or electron passes through one slit. Then some of the energy of the extended electromagnetic field passes through the other slit, and this energy interferes with the photon or electron energy that went through the opposite slit. This is why a photon or electron can interfere with itself. The mystery of the infamous double slit experiment is no longer a mystery. That brings us to the end of the Primer Fields Part 3. I am currently planning a total of 7 installments to properly cover the basics of the primer fields and the implications they have on our world. So we have 3 down and 4 to go. In this installment of the primer fields, we learned about photons of electromagnetic radiation and the electromagnetic fields that surround them. We saw the true cause of constructive and destructive interference. It was shown that when the electromagnetic fields of the same polarity line up, we have constructive interference and the photon glows more brightly. Then we saw that when electromagnetic fields of the opposite polarity line up, they cancel each other out and thereby dim the photon. This we learned is the true reason behind destructive interference. We saw how a sharp edge could cause photons of light to diffract around the edge and give us the intriguing interference patterns we see here. We examined slit diffraction, 1 photon at a time. The reason that light slows down in glass and then accelerates back to full speed on exiting the glass was shown. Then we saw that we could now explain this optical fiber whip due to the fields of the photons pushing off of the end of the optical fiber as the photons exit the fiber. The true reason that light refracts as it enters and exits glass was revealed. We saw that the angle of refraction for photons is determined by their field size. So the next time you see a rainbow, you will know the science behind its beauty. Then we ended by solving the long-standing mystery of the infamous double-slit experiment. In the Primer Fields Part 4, we will be discussing the structure of matter down to the subatomic level. Now it's going to get really interesting.